Welcome to this problem walkthrough. Today, we'll dive into problem number 1024, video stitching. This problem challenges us to combine overlapping video clips efficiently to form a complete video. It's a classic example where greedy algorithms shine. Let's explore the solution together. In this problem, we are tasked with determining the minimum number of video segments required to create a continuous video that covers a specific time range. Each video segment is represented by a pair, start_i, end_i, where start_i is the time the segment starts, and end_i is the time it ends. These segments can potentially overlap, and we need to stitch them together to cover the entire range, 0, time. If it is not possible to fully cover this range, we return -1. The input consists of two parts, a list of clips, which contains all the video segments, and an integer time, which represents the target duration we want to cover. The output is the minimum number of clips required to achieve this, or -1 if the range cannot be covered at all. Let's consider the first example. Here, the input consists of clips equals 0, 2, 4, 6, 8, 10, 1, 9, 1, 5, 5, 9, and time equals 10. To cover the range 0, 10, we can use the following clips: 0, 2, to cover the range, 0, 2, 1, 9, to cover 2, 9, and finally, 8, 10, to complete the range, 9, 10. In total, this requires 3 clips. Therefore, the output for this example is 3, as this is the minimum number of clips needed to fully stitch a continuous video for the given time range. Now let's examine another example. Here, the input is clips equals 0, 1, 1, 2, and time equals 5. In this case, we notice that the clips provided only cover the range 0, 2. There are no additional clips to extend the coverage beyond this point, making it impossible to reach the target time of 5. Since the range 0, 5 cannot be fully covered with the given clips, the output for this example is -1. In the third example, the input is clips equals 0, 5, 6, 8, and time equals 7. The first clip, 0, 5, covers the range 0, 5, but there is a gap between the end of this clip and the start of the next clip, 6, 8. Because of this gap at 5, 6, it is not possible to create a continuous video that covers the full range, 0, 7. As a result, the output is -1, indicating that the target range cannot be fully covered with the provided clips. When solving this problem, there are a few important constraints and edge cases to consider. First, if no clips are provided, it is impossible to cover any range, so the output should be -1. Second, if there are gaps between clips, the range cannot be fully covered. Third, if a single clip is long enough to cover the entire range, 0, time, the output should be 1. Additionally, if multiple clips overlap, the solution should aim to minimize the number of clips used to achieve full coverage. Lastly, if the target time is smaller than the total range covered by the clips, the solution should still prioritize using the minimum number of clips to meet the target. These considerations help ensure that the solution is both efficient and accurate for all possible inputs. To solve the problem of video stitching, we need to ensure that we cover the entire time range from 0 to t using the minimum number of clips. Different approaches can be applied, each with its own trade-offs. One approach is the brute force method. The intuition here is to generate all possible combinations of video clips, checking each subset to see if it covers the target range. Among all valid subsets, we would select the one with the smallest size. While this method is easy to conceptualize, it comes with a significant drawback: its time complexity is exponential, 2 to the power of n, due to the need to compute all subsets. This makes it computationally impractical for larger inputs, as the number of subsets grows exponentially with the number of clips. While it's a starting point, brute force is not feasible for real-world applications of this problem. A more systematic approach involves using dynamic programming, or DP. In this method, we define a DP array where each element, dp, t, represents the minimum number of clips needed to cover time t. The process begins with dp, 0, set to 0, as no clips are required to cover the starting point. We then fill the array incrementally, updating dp, t, using the minimum number of clips required to extend coverage from a valid starting point within the range of any clip. If the target t is reachable, we simply return dp, t, otherwise, we return -1. This approach has a time complexity of O, t asterisk n, where t is the target time and n is the number of clips. While DP is systematic and ensures accuracy, it may become inefficient for large target times, as its performance depends heavily on the length of the time range. The greedy algorithm provides a more efficient solution by focusing on selecting the clip that extends the current coverage the farthest at each step. The process begins by sorting the clips based on their start times. 2 pointers are used, one to track the farthest end reached so far, max end, and another to track the end of the currently selected clip, cur end. As we iterate through the sorted clips, if a clip starts beyond the current end, we increment the clip count and update cur end to max end. If no clip can extend coverage, the algorithm terminates early with a result of -1. The process continues until cur end reaches or exceeds the target t. This approach is efficient, with a time complexity of O, n log n, due to sorting, followed by a linear traversal. Compared to DP, greedy avoids unnecessary computations and handles larger inputs effectively. This efficiency, combined with its simplicity, makes greedy an excellent choice for solving this problem. The greedy algorithm is chosen over other approaches for several reasons. First, it is more efficient, with a time complexity of O, n log n, compared to the O, t asterisk n, complexity of DP, making it faster when dealing with large target times. Second, it uses constant memory, unlike DP, which requires additional space proportional to the target time t. Lastly, once the intervals are sorted, the greedy method is straightforward to implement. However, it does require careful attention to edge cases, such as gaps in coverage or unsorted inputs. In contrast, while DP offers more flexibility for handling additional constraints, its overhead makes it less practical for this specific problem. As for brute force, its exponential complexity renders it impractical except for very small inputs. Overall, greedy strikes the best balance between speed, simplicity, and resource efficiency, making it the optimal solution for video stitching. The video stitching problem asks us to determine the minimum number of video clips required to cover a target interval from 0 to t. Each clip is defined by its start and end times, and we are not allowed to trim or modify these clips. If it's not possible to cover the entire interval, the output should be -1. To solve this problem efficiently, we use a greedy algorithm. First, we represent the problem by defining the input as a list of clips and the target time t. The output is either the minimum number of clips needed or -1 if it's impossible to achieve the coverage. Next, we sort the clips by their start times, and if 2 clips have the same start time, we sort by their end times in descending order. This sorting step is crucial because it allows us to process the clips in a structured way, making it easier to select the optimal clip at each step. For example, sorting the input clips 0, 2, 1, 5, 1, 3 results in the same order 0, 2, 1, 5, 1, 3, which is now ready for processing. To begin solving the problem, we initialize 3 key variables. The first is current_end, which tracks the farthest point we've covered so far. Next, we have farthest, which represents the farthest point we can reach with the clips we're currently considering. Finally, we use count to keep track of how many clips we've used. These variables help us monitor progress and make decisions at each step. Now, we iterate through the sorted clips. For each clip, if its start time is greater than current_end, that indicates a gap in coverage, meaning it's impossible to cover the interval, so we return -1. However, if the clip starts within or before the current coverage, we update farthest to be the maximum of its end time and the existing farthest. This ensures we're always extending our coverage as much as possible. If at any point current_end is greater than or equal to t, we can stop processing because we've already covered the entire interval. Once we've processed all the clips within the current coverage range, we increment the count variable to indicate that we've used another clip. We then update current_end to the value of farthest, effectively extending the range we've covered. This process continues until we either cover the entire interval or exhaust all the clips. At the end, we check if current_end is greater than or equal to t. If it is, we return the value of count, which represents the minimum number of clips needed. If not, we return -1 because it means the target interval couldn't be covered. The greedy approach works well here because we always prioritize the clip that extends the coverage the farthest within the current range. Sorting the clips helps us make these decisions in a logical order. Additionally, we use early stopping to save computation time whenever the target interval is already covered. Finally, we handle edge cases such as no clips, gaps in coverage, or cases where a single clip can cover the entire interval. To implement this solution, we rely primarily on arrays and a few variables. The array stores the sorted clips, allowing us to iterate through them efficiently. The three variables, current_end, farthest, and count, help us track the state of the algorithm and make greedy decisions. Arrays are an ideal choice here because they provide constant time access to elements and allow for efficient in-place sorting. When it comes to complexity, the sorting step is the most expensive, taking n*log n time, where n is the number of clips. Iterating through the clips takes linear time, or n. Combining these, the overall time complexity of the algorithm is n*log n. In terms of space, since the sorting is performed in place, the space complexity is 1, excluding the input storage. This makes the solution both time and space efficient. Let's walk through an example to solidify our understanding. Given the input clips 0, 2, 1, 5, 1, 3, and t equals 5, we start by sorting the clips. In this case, the sorted order remains 0, 2, 1, 5, 1, 3. Next, we initialize current_end to 0, farthest to 0, and count to 0. We process the first clip, 0, 2, which extends farthest to 2. We then update current_end to 2 and increment count to 1. Moving on to the second clip, 1, 5, we find that it extends farthest to 5. We update current_end to 5 and increment count to 2. At this point, current_end is greater than or equal to t, so we return 2, which is the minimum number of clips needed to cover the interval. This example highlights how sorting, variable tracking, and greedy decisions come together to solve the problem efficiently. This Python implementation solves the LeetCode problem number 1024, video stitching, using a greedy algorithm. The goal is to cover the interval, 0, t, using the minimum number of video clips. The function begins by sorting the clips list based on their start times, and if two clips have the same start time, the one with the later end time is prioritized. This ensures we process clips in order and maximize the coverage at each step. Next, three variables are initialized, max_reach, which tracks the furthest point reachable at the current step, end, which marks the endpoint of the currently stitched segment, and count, which keeps track of the number of clips used. The algorithm iterates through the sorted clips. If the start time of a clip is greater than max_reach, it means there is a gap in coverage, and the target interval cannot be fully covered, so the function returns -1. If the start time of the current clip exceeds the end of the current segment, it means we need to extend the stitched segment. In this case, the count is increment, and the end is updated to max_reach. If at any point the end of the stitched segment reaches or exceeds t, the function returns the count, as the entire target interval is covered. Lastly, after processing all clips, if the end is still less than t, the function returns -1 to indicate that it's impossible to cover the target interval. Otherwise, the count is returned, representing the minimum number of clips used. Here, we start with the Java implementation of the video stitching problem. First, we import the necessary libraries and define our solution class. The method, video stitching, takes an array of clips and the target time t as input. The first step is to sort the clips based on their start times. If two clips have the same start time, we sort them by their end times in descending order. This ensures that we prioritize clips that cover more range when their start times are identical. Next, we initialize three variables. MaxReach keeps track of the furthest point we can reach with the current set of clips. End represents the end of the current video segment, and count tracks the number of clips we've used so far. Then, we iterate over each clip in the sorted array. For every clip, we extract its start and finish times. If the start time of the current clip is greater than MaxReach, it means there's a gap we cannot cover, so we break out of the loop. If the start time of the clip is greater than the current end, it means we need to extend our coverage. At this point, we increment the clip count and update end to MaxReach. This ensures that we're moving forward in the range we're covering. Now, we check if the current end already covers the target range t. If it does, we return the count of clips used so far because we've successfully covered the entire range. Otherwise, we continue to update max reach by taking the maximum of its current value and the finish time of the current clip. This step ensures we're always aware of the furthest point we can reach with the clips available. Finally, after exiting the loop, we return -1 if the end is still less than t, indicating that it's not possible to stitch the clips to cover the entire range. Otherwise, we return the total count of clips used. This approach ensures that we efficiently solve the problem while minimizing the number of clips required. To solve the video stitching problem, we start by taking the list of video clips and sorting them. They're sorted first by their start time, and if two clips have the same start time, by their end time in descending order. This ensures we can process them in a logical sequence. After sorting, the list of clips becomes 02, 15, 28, 46, 59, 810. Next, we initialize three variables, max_reach to track the furthest point we can reach in the current step, starting at 0, and to represent the endpoint of the current video segment, also starting at 0, and count, which keeps track of the number of clips used so far, starting at 0. Then, we begin iterating through the sorted clips. For the first clip, 02, since its start time of 0 is less than or equal to max_reach, it's a valid clip. Because its start time is greater than end, we extend the coverage by incrementing count to 1 and updating end to max_reach, which is now 2. Finally, we update max_reach to the larger of its current value or the clip's end time, resulting in max_reach equals 2. Next, we process the second clip, 15. Its start time of 1 is less than or equal to max_reach, so it's valid. We then update max_reach to the larger of its current value or the clip's end time, which gives us max_reach equals 5. Moving to the third clip, 28, its start time of 2 is also valid for max_reach. Again, we update max_reach, which now becomes 8. For the fourth clip, for a 6, we see that its start time of 4 is greater than end, meaning we need to extend coverage. We increment count to 2 and update end to max_reach, which is 8. The fifth clip, 59, is valid because its start time of 5 is no greater than max_reach. Updating max_reach gives us 9. Finally, the sixth clip, 810, is also valid, and updating max_reach results in 10. After processing all the clips, we check if we've covered the target range. At this point, end is 8, which is less than the target value of 10. To extend coverage, we increment count to 3 and update end to match max_reach, making end equals 10. Since end is now greater than or equal to the target value of 10, our target range is covered. The minimum number of clips required for this example is 3. This demonstrates how we use sorting, iteration, and the greedy approach to determine the solution. Now, moving to a new example with clips 01, 12, 23, 34, and a target T of 5, we follow the same process. After sorting, the clips remain in the same order 01, 12, 23, 34. We initialize max_reach end and count to 0. Starting with the first clip, 01, since its start time of 0 is less than or equal to max_reach, it's valid. Because its start time is greater than end, we extend coverage. When extending coverage with the first clip, 01, we increment count to 1 and update end to match max_reach, which becomes 1. We then update max_reach to the larger of its current value or the clip's end time, resulting in max_reach equals 1. Moving to the second clip, 12, its start time of 1 is valid for max_reach. Since it starts after the current end, we extend coverage again. This increases count to 2 and updates end to match max_reach, which is now 2. Updating max_reach gives us 2 as well. For the third clip, 23, the start time of 2 is valid. Once again, we extend coverage by incrementing count to 3 and setting end to match max_reach, which becomes 3. Updating max_reach gives us 3. Finally, for the fourth clip, 34, its start time of 3 is valid, and we extend coverage once more. This brings count to 4 and updates end to match max_reach, which is now 4. After processing the fourth clip, we update max_reach to 4. At this point, we check the coverage. The value of end is 4, which is still less than the target value of 5. This means it's not possible to cover the entire target range using the given clips. In this case, the output is -1, indicating that no solution exists. This example highlights a scenario where the clips, despite being valid individually, are insufficient to cover the entire range. Finally, let's analyze another example with clips 0, 4, 2, 8, and a target T of 5. Following the same process, we first sort the clips, which results in 0, 4, 2, 8. We initialize max_reach end and count to 0. Processing the first clip, 0, 4, its start time of 0 is valid. Since it starts after end, we extend coverage, incrementing count to 1 and updating end to match max_reach, which becomes 4. Updating max_reach gives us 4 as well. Next, we process the second clip, 2, 8. Its start time of 2 is valid for the current value of max_reach. We update max_reach to the larger of its current value or the clip's end time, resulting in max_reach equals 8. At this stage, we check the coverage. The value of end is 4, which is less than the target value of 5. To extend coverage, we increment count to 2 and update end to match max_reach, which becomes 8. Since end is now greater than or equal to the target value of 5, the target range is covered. The minimum number of clips required for this example is 2. This demonstrates how the greedy approach efficiently selects clips to cover the target range while minimizing the number of clips used. To analyze the time complexity of the solution, let's break it down into its two main components. First, the clips list is sorted based on the start time of each clip, with ties resolved by sorting the end time in reverse order. This sorting step is the most computationally expensive part, and it takes n*log n time, where n is the number of clips. After sorting, we iterate through the clips list to determine the minimum number of clips required to cover the range, 0t. This iteration involves a single loop, so it runs in n time. Within the loop, operations such as comparisons and updating variables like max_reach are constant time operations, or O1. When we combine these, the sorting step dominates the overall time complexity, so the total time complexity of the solution is n*log n. Now, let's analyze the space complexity of the solution. The clips list is provided as input, and the algorithm does not create any additional copies of this data, so no extra storage is used for the input. The sorting operation, depending on the implementation, may require auxiliary space. Python's built-in sort method uses timsort, which has a worst-case space complexity of n for auxiliary storage. Additionally, the algorithm uses a few scalar variables, such as max_reach end and count, which require only O1 space. Combining these factors, the dominant space usage comes from the sorting step. Therefore, the overall space complexity of the solution is n. Next, let's evaluate the complexity in different scenarios. In the best case, the clips are already sorted, and the first few clips immediately cover the range, 0t. While sorting still takes n*log n time, the iteration is minimal, approaching 1, though the overall complexity remains n*log n. In the average case, where the clips are randomly distributed, the solution requires sorting and a full pass through the list. This results in n*log n time. In the worst case, there is no valid solution, such as when there is a gap between the clips. In this scenario, the loop iterates through all the clips and ultimately returns -1. Even in this situation, sorting still dominates, so the time complexity remains n*log n. Finally, let's compare this solution to a brute force or naive approach. A naive method might involve generating all possible combinations of clips to check if any subset covers the range, 0t. This would result in an exponential time complexity of 2 to the power of n, due to the number of subsets, which becomes infeasible as n grows. The given solution avoids this inefficiency by adopting a greedy strategy. Sorting the clips ensures they are processed in a logical order, and tracking variables like max_reach allows the algorithm to extend coverage without redundant checks. After sorting, the problem reduces to a single pass through the list, achieving n*log n time. Because sorting dominates the time complexity, we can mathematically confirm that the overall complexity is O, n asterisk log, n, for time and O, n, for space. On this slide, we're discussing some common mistakes that can trip up developers when solving the video stitching problem. First, sorting the video clips by their ending times instead of their starting times is a frequent error. The greedy approach hinges on extending the interval as far as possible from the current start, so sorting by end times breaks this logic. The correct approach is to sort by start times first, and if two intervals have the same start time, sort by their end times. Next, failing to account for gaps in the intervals is another pitfall. Assuming all intervals are seamlessly connected can lead to incorrect solutions. Always verify that the current interval starts at or before the end of the last covered time. Finally, overcomplicating the solution by using dynamic programming or other complex algorithms is unnecessary here. A properly implemented greedy approach is optimal, both in terms of simplicity and efficiency. Avoid adding extra layers of complexity that don't enhance the solution. Now, let's look at two more mistakes to avoid. First, failing to handle edge cases can lead to solutions that break under specific conditions. For example, if there are gaps in the intervals or if the first clip doesn't start at time 0, the solution might fail. Always ensure your algorithm includes checks to confirm full coverage, starting from 0 and reaching the target end time. Another issue arises when modifying the input list during iteration. Changing the list while iterating over it could lead to runtime errors or skipped intervals. To avoid this, work on a sorted copy of the list or use indexes to iterate safely. These precautions will help you maintain the integrity of your solution and handle edge cases robustly. When solving this problem in an interview, there are several key areas to focus on. First, demonstrating mastery of the greedy algorithm is critical. You should be able to explain why the greedy approach is appropriate and how it ensures optimal results. Interviewers may also ask you to analyze edge cases, such as handling non-overlapping intervals, redundant intervals, or cases where intervals exceed the target range. They might probe your understanding of complexity trade-offs, asking why other approaches like dynamic programming are less efficient for this problem. Additionally, be ready for follow-up questions that introduce variations, such as minimizing the number of intervals used or solving the problem in real time with streaming input. These follow-ups test your adaptability and depth of understanding, so be prepared to think on your feet. This problem is closely related to several others in LeetCode that also focus on greedy algorithms and interval manipulation. First, of course, is LeetCode 1024, the video stitching problem itself, which directly tests your ability to solve this challenge. Next is LeetCode 55, the jump game, where you use a similar greedy approach to determine if you can reach the end of an array. LeetCode 45, Jump Game 2, builds on this by asking you to minimize the number of jumps needed to reach the end. Finally, LeetCode 435, Non-Overlapping Intervals, focuses on removing the minimum number of intervals to make a set non-overlapping. These problems all share common themes, and practicing them will strengthen your understanding of greedy algorithms and interval-based problem solving. Finally, while the greedy approach is optimal for this problem, let's briefly explore some alternative methods and their trade-offs. Dynamic programming is one such approach. Here, you could use a DP array where each element represents the minimum number of clips needed to cover up to a specific time. However, it comes with higher space and time complexity, making it less efficient compared to greedy. Another option is the sliding window approach, where you track the maximum end time achievable within the current window. While effective, it's slightly more complex to implement and debug. Lastly, a breadth-first search (BFS) approach treats the intervals as nodes in a graph and searches for the shortest path to cover the target time. While this ensures all possibilities are explored, it's much less efficient and intuitive than greedy. These alternatives can be useful in specific scenarios, but for this problem, the greedy method remains the most practical and efficient choice. Great job making it to the end. To summarize, we solved the video stitching problem with a greedy approach, focusing on minimizing the number of clips to cover the range. Remember, greedy algorithms are an excellent choice for interval problems like this. If you enjoyed this walkthrough, be sure to like and subscribe for more problem-solving tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!